Let's practice computing the change in internal energy for an ideal gas system. So we're told that an ideal gas is heated at constant specific heat. That means the specific heat does not change over the temperature range under consideration. Not generally true, but in this problem it is. We want to know its change in internal energy. Okay, not enough information yet. Now we're told the initial temperature is 300 Kelvin and the final is 375. The specific heat at constant pressure we're given as 0.48 kilojoules per kilogram Kelvin. The mass of our system is 5.0 kilograms. The molecular weight of our system is 70 kilograms per kilomole, whatever that corresponds to. And of course we know the value of R bar, the constant. That's true for any gas. So here's the parcel of ideal gas, and we want to know its change in internal energy. That's delta big U. Okay. So we'll start by writing the relationship between delta big U and delta little u, the change in specific internal energy. Well, that's pretty straightforward. They're related by a factor of mass. For delta little u, here's where we can use one of the equations that's appropriate for an ideal gas, namely that delta little u is the integral over temperature of the specific heat at constant volume. So you need to pay attention to the subscript. We have Cp, but the integral that we need to use involves Cv. Okay, so we can substitute that in. Delta big U equals just mass times that integral. Fortunately, for an ideal gas, there's a very simple relationship between Cp and Cv. This is true even if they're varying over temperature, namely that Cp equals Cv plus R, the specific gas constant for this gas. So we can rearrange that and solve for Cv in terms of Cp and R, and we can plug that back into the integrand in our equation for delta big U. So we say now that delta big U is mass times the temperature integral of Cp minus R. You can see that I've written it generally so that this would still be true even if the specific heat varied with temperature. But of course, in our givens for the problem, it does not vary with temperature. R never varies with temperature for a particular substance. So we can actually pull Cp minus R out of the integral. Well, that's pretty nice. So now we have a bunch of constants, mass times the quantity Cp minus R, and then the integral of dt. Integral of a differential is an integral I can do. That becomes delta U equals m Cp minus R times the temperature difference. So we'll move that up to the top. The last step before plugging in numbers is that we need a value for R, the specific gas constant. We have R bar, the universal gas constant. Fortunately, those are related through m, the molecular weight, so R equals R bar divided by m. We can just substitute that into our expression. So now we have an expression where we know all of the variables on the right-hand side, and we can solve for delta big U. So I'm going to plug everything in at once. There we go. All right, let's simplify this a little bit. So it's still going to be 5 kilograms. I'm going to simplify the stuff in brackets in the middle to 0.361 kilojoules per kilogram Kelvin. You'll note that that actually should be the value of Cv, right? Because Cp minus R was Cv. So now we indirectly solved for it. And then the temperature difference is just 75 Kelvin. We can check the units here, make sure we didn't make any major screw-ups. Cancel kilograms, cancel Kelvin. We should get out a delta U in kilojoules, which is fine. So delta big U is 135 kilojoules.